All right, this is section 4.5, day 1, and today we're going to start graphing sine and cosine functions. We're going to start off by graphing the sine function, and learning this is kind of like learning the parent function. So when we get done doing this, this is kind of the graph that you need to know. You need to know its shape, how it starts, how long of a function is, all of those main points. We're actually just going to use our unit circle, and I'm going to pick off all the really good y values to use. So when we're graphing sine, that is a y value. So I'm going to look for really easy y values to graph. Here's a really easy y value. So at 0 degrees, my y value is 0. These aren't bad. I mean, I don't want to graph square root of 3 over 2. I mean, even 1/2, that's okay. But if I go to 90 degrees, I actually have a y value of 1. That's a little easier to graph. Then at 180 degrees, I'm at 0 again. 270 degrees, I'm at -1. And then circling, finishing it, will be 360 degrees, and I would be a 0 again. So just plotting these, I've got 0, 0. I'm going to let this be 1 and this be -1, just to kind of space it out, give me a little space. At 90 degrees, I'm at +1. At 180, I'm 0, -1, and then back to 0. So this is what a sine function looks like. Nice and curvy. Make sure it looks like a nice roller coaster. And then we're just going to keep the pattern going on the other side. So this is not a mirror. It doesn't go up right here. I wouldn't want a sharp turn like that in terms of a roller coaster. So if we're starting here and we go down, and then we're up, and then we're down, and then we come back up. So we want to keep that pattern going of my roller coaster. So that is your basic sine function. Starts at 0, 0, or starts at the middle and heads up. Makes kind of like one good S shape before it starts repeating itself again. So a maximum point on sine happens at pi over 2. There's actually another one happens there. And if we kept graphing this to the left and to the right, there would be a lot more. There would actually be an infinite number. So we're going to say we start at pi over 2, and then we're going to say every plus and minus 360 after, oops, sorry. I started in radians, I should stay in radians. So we should say 2 pi, plus or minus 2 pi after that. So every loop around the circle will get me back to a highest place. If I was at 90 degrees, which is the highest place, to get there again, I would have to go around 360 degrees. So every 2 pi, I will hit another high place. The minimum happens at 3 pi over 2. That's just one of them. And then again, plus or minus 2 pi. To get to another low spot, I'd have to travel an entire 2 pi, one revolution of the circle, 360 degrees. I would have to travel that once in order to hit another low place. The intercepts are just like the x-intercepts, so we're just talking about all these places where it hits. And it hits actually twice as often as the highs and lows, because every time I travel from one to the other, I have to go through the x-axis. So we'll start at 0, and then it'll be plus or minus pi after that, so it hits more frequently. The domain, range, and period are very interesting. They are the same for both sine and then the cosine function. The domain here is just talking about what kind of x values can you have. You can have anything. You can have negative angles, positive angles, decimal angles, fraction angles. You can do them all. The interesting thing is that the range can only be between 1 and -1. So no matter what angle you pick to plug in, the values you get top out at +1 and bottom out at -1. That's it. The period, then, that's a new kind of word for us. It's used when we do trig, because we were talking about the amount of time it takes to repeat. Some people call that like one cycle of the graph. So one period of the graph is the amount of time it takes to repeat. So we're talking about going from a high to a high, or a low to a low, or a middle to a middle, both of them heading upward. So anywhere, if I pick anywhere on this circle, the next time I could be at that point is if I go around 360 degrees. So a period for us is 2 pi on the sine function. We're going to do cosine the exact same way. I'm going to use all the x values of really nice angles. So the first really nice angle is at 0 degrees, and that x value is 1. Up at 90, that is 0. 180 is -1. 270 is 0. And 360 is 1. So we're going to plot those looking very reminiscent of all of our sine values. Like they changed a little bit, like they're all off of what what sine was. So when we graph these, 0, again, I'm going to have that be a 1 just to kind of spread my graph out a little bit so it's not tiny. 90 degrees would be 0, 180 would be -1, 270 would be 0, and then 360 would be 1. So this graph looks a little more like that, more like a U. Make sure that you turn that back down because it's going to come down from there. To keep the pattern going, we would hit 0, low, and then 0, and then high again. So here we go. And again, turn your arrow down so it tends down. And they actually are essentially the same function. One of them is just shift from the other one. So if I could pick this cosine function up and actually slide it 2 places to the right, I'd have the same graph as that one. If I could move that point over, they'd be the same. Or if I moved that one over, that would be a cosine graph. So they are each other's graph, they're just shifted a little bit. So what changes is the max, min, and intercepts, but the domain, range, and period are the same. So the maximum point happened at 0, and it'll happen every 2 pi after that. Your minimum happens at pi, and it happens every 2 pi after that. And then your intercepts, they happen more frequently than 2 pi. So the first one happens at pi over 2, and then pi after that. So that's what our 2 parent functions look like, our sine and our cosine graph. Do need to know what they both look at their base as a parent. So being that sine starts in the middle of its curve and is heading upward, cosine starts at the top of its curve and is headed downward. So kind of just starting off that y-axis. Let's talk about what the equations look like for trig. So this is their basic setup. I apologize. I changed this in your notes packet and didn't change it in mine. The B is out there. So this is the basic setup where all of the numbers are located, and it looks really reminiscent of when we were doing parabolas even. So this D number on the end, that is a vertical translation that moves the graph up and down. And you move up and down based on what that number is. So if you want to move down, the number will be negative. If you want to move up, the number will be positive. So if you can see it on your notes packet, it's pretty faint, but the original function, the parent function, is really light. And then it looks like we've moved it down 1 to get to the black function. So that's a vertical translation. That would come from a D value. C we know to be our horizontal translation. Even when we were doing parabolas, if we had a number inside with the x, that would move it left and right. And if you want to move left, you actually had to be positive. And if you want to move right, you had to be negative. So you're doing the opposite. So this would be a horizontal shift. Here's the original parent function. That's a cosine. And it looks like they were moved over that way. So the light gray graph shifted left for the black graph. These two are kind of interesting. They're a little more specific to just trig. The A is called the amplitude. This is the height of the bumps. So how much space from the middle, how tall are these bumps? So the original function is a height of 1 right there. Height of 1, height of 1. Even though it goes downward, the height is still 1. And then it looks like the next one now has a height of 2. Looks like we were just stretched out. So the amplitude would be 2. You're just talking about the space or how far it is from the midline out to the top or bottom of the graph. If A is negative, it just means that you have a flip. And I'm going to say over the x-axis or the theta axis, they're kind of interchangeable here. The B value is very interesting. If there is one that students get wrong on the test, it is B. So B has to do with your period, and I call it the slinky effect. So if you had a slinky when you were a kid and you think about pulling your slinky apart and making it really flat, or you push your slinky together and you have a lot more bumps, that's kind of what I mean by the slinky effect. There is a little equation for B. If we know B, it is 2 pi over period. That's how it affects it. Or conversely, then period would equal 2 pi over B. So whichever one you have, you just do 2 pi divided by it to find your other one. And it is all about affecting your period. Is your slinky stretched out or is your slinky smushed together? If B is negative, you have a y-axis reflection. We won't do any of that kind. I just wanted you to know that they exist. So let's try a couple of these. First few, just say, what is the amplitude? Amplitude is located in front of the function. So the amplitude here is 3. This one is 2/3. This one's a little tricky. The amplitude is just 1. The negative is actually a flip, and that has nothing to do with the amplitude. The negatives just happen to sit out front, so it looks like they belong with the amplitude, but they are separate. Amplitude for this is 1. The negative is the flip. What's the period of each of these? Remember, you cannot find period by looking at the equation. It has a little equation in order to figure it out. So 2 pi divided by B is the period. B is always found in between the trig function and the variable. So in this instance, it'll be 2 pi over 1, so period is just 2 pi. This one is 2 pi over 3, so that's my period. This one is 2 pi over 1/4, which is weird. So we'll flip the bottom, bring it up, and you'll end up with 8 pi. So this is a shrunk period. You are squeezing things into a 2 pi over 3. That's less. And then this is a long, like, stretched your slinky out. So it's a real, I shouldn't say shallow, a real slow graph. Like, you don't get a lot of action in 8 pi because you've pulled the slinky apart. What is the shift? When there's a number inside, it shifts to the right or left. This one's right because it's negative. This 6 moves you up 6. This 1 moves you left 1 and then down 3. The last two, we're just going to put all these pieces in where they belong. So amplitude goes first. Vertical shift goes on the end. Period is pi over 2. Remember, you do not have... Nope, sorry. You have the period. We want to find the b. Period is not what goes into the equation. So we're always doing 2 pi divided by whatever we get to find the piece that we need. If we have the equation, like up here, we have to divide in order to find the period. And if we have the period, we have to divide in order to find the b. So I'm going to times by 2 over pi, bring that up. So I have 2 pi times 2 over pi. So pi's will cancel, and I'll end up with a 4. Right now, it doesn't matter if you use sine or cosine. We will talk tomorrow or in the next lesson about how that works. So I'm just going to pick sine. Again, it doesn't matter. Throw a theta or an x in there. That's your variable. And then that is your equation. Next one, y equals 3 is the amplitude. Looks good. I'll pick cosine this time. Again, it doesn't matter for right now. It will later on. I have a horizontal shift of -2. So I'm going to have to put that in as a +2 in with the x. I have a period of 2 pi that is not my b. My b would be 2 pi over 2 pi, which is 1. And then I have a flip, which means I need to get a negative in front of the whole thing. So that is just the first day on trig functions, what their equations look like, how each of the numbers move the graph.